Hello and welcome to another episode of Electronic Savvy. In this episode, we're going to talk about LTspice. Whether you're a seasoned electronics designer or just getting started with circuit simulation, LTspice is an incredibly powerful tool that can help you bring your designs to life. With LTspice, you can easily simulate and analyze complex electrical circuits, test out different designs and components, and get a detailed view of how your circuit will perform in the real world. And the best part, it's completely free and available for download online. I leave the download link in the video description. So in this video, we'll take a closer look at how LTspice works and walk you through some of the key features and tools that you'll be using in your design. So for the Mac users, when you open up LTspice, this is the first page that kind of comes up. It's the draft one. It's the complete empty schematic, nothing on it. And the way that we interact is pretty simple. You can use your keyboard or your mouse and you could right click and you have a couple options. First one is run. That's when you create a circuit and then you hit run to basically run the circuit. You have view. In view, you have a couple options. This is to zoom to fit if you have a large circuit, for example, or if you've been out of focus. If you click this button, it'll basically zoom to fit. You could have grid dots where it basically just creates a dotted sheet instead of a plain sheet. I prefer the plain sheet. That's why I just keep it plain. I just feel like it looks a little cleaner. And when you go to view, there are a bunch of other options here that we're going to get to a little bit later, but there are Spice net list. This one is basically lists all the nets that you'll create in your circuit. We have bill of materials. This is again all the part numbers, values, designators, and everything in your circuit. And there is an efficiency report, which is mostly used for converter design. Let's say you have a DC-DC converter, you could use this efficiency report to get efficiency value of your circuit. And then you have edit. In edit mode, you have a couple options. You could move, you could drag, delete, duplicate, and undo. These are all the shortcuts that basically Mac users can use on your keyboard, F7 and F8. I find it pretty helpful to just use shortcuts instead of using just this drag down menu. And then for draft, this is probably the main feature that we use when we use LTspice, which is to draw wires, to place components, create net names. Spice Directive is the tool that enables us to do multiple different versions of simulations. For example, transient DC analysis, AC analysis, logarithmic analysis, or just DC operation point analysis, which is the simplest form of this. We're going to get to this in a little bit later. And then comment text is that you could just have like a comment. And then for draw, you could create lines and circles in your schematic. You could draw those. Now, first, let's start by taking a look at this simple circuit diagram. With LTspice, you can quickly and easily create a schematic of your circuit and then simulate it in real time to see how it performs. Again, the keyword here is real time. And for this simulation, we're interested in how does this circuit actually behaves in real time. That's why we run this .tran directive, which is a transient analysis, which is a time-based analysis, right? So this simple circuit is basically a voltage divider circuit. Let's say you have a 12-volt battery and you want to create a 5-volt output to use, for example, as a reference in your ADC, which is an analog to digital converter, or you want to use it to power an LED or anything else. So let's say you want to create this 5-volt. Again, this is a pretty straightforward circuit where you select the R1 and R2 values based on your input voltage as well as your output voltage. So in this case, I set my output voltage to 5 volts and I have my battery voltage or input voltage set to 12 volts. So that's how I found these two values that are actually a standard resistor value that will output a 5-volt DC. So now let's talk about how do we create a circuit like that. So in LTspice, as I said, the easiest way to interact with this sheet is using your keyboard. So in order to place components, what we could do is we could hit F2 if you're a Mac user, and LTspice basically has an embedded libraries of parts that it basically put together and it gets updated every other week. So we're just going to look for a resistor. So if you just type out resistor, the resistor pops up, and then when you hit OK, it basically pops up right in your schematic sheet. You can move it around to place it. If you just hit the left key on your mouse, it'll basically just place it for you. So that's one way to do this. The other way, which is an easier way, for resistors, you could basically just hit key R on your keyboard and resistor just pops up. All passive components can use a simple key on your keyboard to be placed on the schematic sheet. So here we have the resistor. So that's how I place a resistor here. And if we hit F2 again, we can look for a voltage source, which again, the voltage source comes up. So we hit voltage source, and that's how we get the voltage source. Similar thing, if we go hit current source pops up, and then that's how we have this current source over here. And every circuit that you design in LTspice needs to have a return path, or ground in this case. So in order to place a ground, you could just hit G on your keyboard and a ground symbol will pop up that indicates the ground or return path of this particular circuit that you designed. So let's say you place this resistor somewhere on your circuit. How do you change the value on this? The way that you change the value of this resistor is you just hover around it and you see this little finger that pops up. And then if you right click, this box opens up which says resistance value. So that's how you put resistance value. Let's say in this case I want to have 1000 ohms. You could either just type out 1000, or you could just use the acronym of 1000, which is just a K. So you could just use 1 kilo ohm, which is just much simpler, and it's not gonna dirty up your sheet. So you could hit 1K, and now your resistor has this value of 1K. Again, resistors in real life, they have tolerances, they have some variation with temperature and different parameters that LTspice doesn't actually just consider them. So that's why it's important to note that LTspice is just a simulation tool, and the actual design might vary a little bit. But if you want to have a more real resistor, you could hit this pick a standard percent value, and then here it basically just tells you all the real values depending on the tolerances that you have for this resistor. Again, tighter tolerances like 0.1% is generally a bit more expensive than, for example, 5% resistor. So that's why there are different values around that 1 kilo ohm. But 1 kilo ohm is a typical value. So we could just go ahead and just stick with the 1 kilo ohm for now. Anyway, so now we have the 1 kilo ohm over here. And let's say I want to remove this part. So the way that we do it is we press F5, and F5, you see this little scissors come up, which is just your delete icon, let's say. You could either just hit on this guy, or if you want to delete multiple parts, you could hold and drag this scissors, and this basically deletes everything that's in that box. Now let's talk about how we connect these components. So let's say we have this resistor, and then now we also have a capacitor, and also we have L, which is an inductor. As I said, all passives in LTspice can be selected by using a single key on your keyboard. So the way that we connect these components together is we use F3. So when you hit F3, this little kind of a cross symbol pops up that enables you to connect all these components. So if you connect these components, you could just press the left key, and then you just drag it all the way down to connect them all. So now once you connect them, LTspice will get rid of the excessive wires that's running through these components, and it's not gonna look any weird. So this is what it's gonna look like. So now that's how you basically connect components in LTspice, which is pretty straightforward, right? So let's now remove all of these extra parts, as I said, and now go back to the circuit that we drew. So this circuit, again, is a pretty standard voltage divider circuit that steps down, in a sense, a 12-volt battery voltage into a 5-volt output that can be used for your analog digital converter, or it could be used to power some LEDs, or it could be used for any other application that only uses a 5-volt supply. So the way that we name these wires is also important. In this case, this is a simple circuit, but let's say you have a complex circuit and you want to make sure that you have well-documented and well-named nets. So the way that we do it is we just hover over the wire that you want to name, and then you right-click and hit Label Net. So once you hit it, Label Net pops up, and this already indicates that it's bad, which is just a battery, and that's why I already named that battery. But you could change it to anything else that you need, like a battery or anything you want, and then just hit OK, and it'll rename the net for you so it makes sense. Same thing here, I just named it out, so when we run the simulation and when we see the plot, it actually makes sense. And again, as I said, we use this equation to select the exact values of these resistors, but it's also important to note that depending on the current that flowing through these resistors, we need to be careful of the power dissipation across each of these resistors, which is given using this equation, I squared R. And again, if we have a lower resistor, like in this case R2 is lower than R1, and since these two are both gonna get the same amount of current through them, surely R2 will have a higher power dissipation compared to resistor R1. And you may ask, why am I adding this I1, which is a current source, across this out pin? The reason for that is this is to model whatever circuit you have connected to the out pin. Again, in this setup, as you know, it's a simple Ohm's law. I set it already to 0 ohms, so there is no current that's flowing out of this out pin to this, let's say, downstream circuit. So it's pretty straightforward based on Ohm's law to calculate the total current that comes out of this supply and gets pumped through R1 and R2, considering that this current source is set to 0. So in this case now, we have about 7 milliamps of current that's going through R1 and R2. Again, these are in series, so they share the same current as depicted by Ohm's law. So now that we have a better understanding of this circuit, let's simulate it. So the way that we simulate circuits in LTspice depends primarily on what you're trying to achieve. In this case, we want to test how the circuit behaves in time domain. In other words, I want to run a transient analysis on this circuit to understand how does this circuit behave at time equals 0 onwards. So that's why I have this model in here, which is a directive in LTspice that is called a transient analysis. And the way that we set this transient analysis is you hit your key S on your keyboard and it's already naming it spice directive. So now you just basically type up .tran, and this will get LTspice to understand that you're trying to run a transient analysis. There are other type of analyses that we can get to in other episodes, but .transient is the main used directive in DC circuits. So we have a .tran, we also have .ac, which is an AC analysis. We also have .op, which is a operational directive, which is the most basic simulation that LTspice runs just to calculate the current through the circuit, the voltages, all the voltages, and everything that you have on your circuit. It basically just types it out in a text file. But in this case, again, like I said, we're going to run a .transient analysis, and the format for .transient analysis is .transient and then space. There are multiple steps in .transient. What I have in here is I just set it to 2 milliseconds, which means that LTspice runs this circuit for 2 milliseconds and stops. So once we create this .tran 2 milli, we go up here and then we hit this run icon. So when you hit it run, this guy pops up. So now we have the circuit on the right and we have our waveform analyzer or the simulation result on the right. The simulation gives you a detailed view of the circuit's behavior. Now let's go ahead and find a particular net or a component to simulate. So in this case, let's say I'm interested in looking at this voltage. So the battery, I want to see what battery voltage is looking like. So the battery voltage is indeed at 12 volts. And let's say I want to know what my output voltage is. Output voltage is indeed set to 5 volts as we discussed. As you can see, output voltage is on the bottom and the battery voltage is on top. So now also let's look at the current through R1 and then current through R2, which again, as we said, it must be equal to each other because we're not sinking any additional current through this source, and it is showing at 7 milliamp, which that's the value it was that we calculated. As you can see, the simulation gives you a detailed view of the circuit's behavior, including voltage levels, current flow, and other key parameters. This allows you to test out different components and designs to find the best solution for your needs. So in this case, what we were mostly interested in was to create a 5 volt output from a 12 volt battery, and that's what we have. And we know for a fact that we are able to sink about 7 milliamps of current at most through, let's say, a small ADC, like I said, that is used as a reference voltage. So another tool that LTspice gives you, which is pretty handy, I feel like, is LTspice allows you to also model power dissipation across every single component. In this case, we're using resistors, but the same thing applies if you have capacitors, inductors, even ICs or transistors. So the way that I like to do it is I like to split the plane in this SPICE simulation tool. So if you go on this window and right click, you have a little box that pops up. There are a couple options, again, zoom to fit, pretty self-explanatory, but you could go to view to create kind of a grid view, which kind of, makes it look like that. Again, it's nice, but it's a little too messy, so I just don't like the grids. But you could have like, FF fast Fourier transforms. You could have, other data points. Again, we don't have steps, but you could create steps. But what I'm interested mostly is I'm interested in creating another plot plane. So when I create another plot plane, LTspice basically creates another window where we could independently plot waveforms. So if I click here, LTspice understands that this is the window I'm interested in. So I go back to my schematic sheet, and then when I hold Alt on your Windows or Command on your Mac machine, this little icon pops up that looks like a thermostat, right? And what this is doing is basically calculating the voltage across this R1, and it multiplies it by the current through R1. So if you hit this, you see that now we get this plot on the upper plot where it's basically indicating that there is going to be about 49 milliwatts of power across this resistor. So what that means is we need to be careful about thermals. We need to be careful that this particular resistor can withstand 49 milliwatts of power. So what that means is we need to make sure that this resistor is sized up properly, that it doesn't overheat and it doesn't burn out. Same thing with R2. You see, as I said in the beginning, R2 is a little bit less. The reason for that is, again, the same equation. We have same current going through R1 and R2. There is a same voltage across R1 and R2 combined, but there is higher voltage drop across R1 because R1 is going from 12 volts to 5 volts and R2 is 5 volts to 0. So you see that the voltage drop across R1 is actually 7 volts and the voltage drop across R2 is 5 volts. And R1 is larger than R2. So the two parameters, when they add up, you get a larger P or larger power dissipation. So that's why it's important, again, to have these understandings of your resistors so you can find the right package size for those resistors. So now let's say we want to connect this out pin to an LED. Right? Let's say you have a 5 volt LED that you want to connect this to, and you're modeling it as this current source. Again, this current source, similar to the voltage source, you could right click and then you could set the DC value of this current. There is another option here that says advanced. So if you click on advanced, you could go to style, and then you see here I have a DC value, but if you click on this drop down menu, you have other options. So you could set this current source to be basically outputting a pulse, sine, or exponential, or other custom waveforms that you can have run on this current source. So again, this is a simple DC operation. I'm not interested in pulses or any sine. So I'm just going to set this DC value to, let's say, 200 milliamp, right? So when I set this to 200 milliamp, what I'm saying is I'm expecting to be able to supply 200 milliamp from this circuit. Let's see if we can sync 200 milliamp from this circuit. So I'm going to keep the same simulation window open, and we're just going to go ahead and rerun this. So now, as you can see on the left, we have VBAT again set to the same 12 volts. And again, in order to actually see the values that's presented here is by just left clicking on each of these names. So if you left click on VBAT, this pops up. Think of it as your oscilloscope knob. So you could basically just move this guy. As you can see here, this little fist kind of comes up that you could just drag this, and it basically just moves it along the time axis that you ran it. And you see from like basically 0 second all the way to 2 milliseconds that we ran it for this transient analysis. The battery voltage is fixed to 12 volts, and we don't expect anything less, right? Same thing with your out. So in this case, out, we expected this to be 5 volts, right? But you see that the out voltage is minus 78 volts, which is pretty odd, right? And you see that like the current through R2 is also negative, right? Negative 109 milliamp, which is pretty odd. And then, but the current through R1 It is about like, right, it's about like 90 milliamps. So why does it happen? So this goes back to the same idea of Ohm's law. In this case, what we did is we created a constant current source. What's that mean is LTspice is modeling a constant current load for your circuit, which means this circuit will have to source 200 milliamp to this load regardless of any condition. So the way that Ohm's law works, you have current and voltage always act in opposite directions. So when you bump up your voltage, you're gonna get less current. When you bump up your current, you're gonna get less voltage. So for your circuit, in order to be able to provide 200 milliamp, what we forced it to do was to change the voltage of the out pin to something drastically different in order to satisfy the 200 milliamp of requirement for the output current load. So that's why that this circuit cannot work very well when it comes to high power applications. This is regardless of all the power dissipation that you can see on top that is happening across these two resistors. There is 8 watts of power loss across this. So you know that these two are getting pretty toasty, right? And this is not an ideal solution. So how can I have a circuit that I can use with this constant current load and I can be supplying enough current without jeopardizing the output voltage? So the way that we could do it is a pretty simple technique. We just gonna go ahead and remove R2, and we're gonna go to our component menu, which is, again, you could right click, you go to draft and then component, or you could just hit F2 and then you look up diodes. So this is what a diode looks like in LTspice, which is pretty conventional. And you can move this diode around, and then you could hit Control R on your Windows machine or Command R on your Mac machine to rotate this component 90 degrees. As you can see, every time I hit Command R or Control R, this component rotates 90 degrees. I can also hold Command and hit E as echo, or Control and hit E in order to flip this component. You can see it flips at 180 degrees. So you have these tools that you could use to move the components around. You can move the polarities. So let's say in this case, I'm just interested in this diode. So I'm just gonna go ahead and place it right over here. And then now I have this diode. So this diode, again, is kind of an ideal diode, that's not what I want, right? So the way that we select it, again, diodes have a PN junction, so they act like a switch. You could use them as voltage regulators. If you use Zeners, you could use them as LEDs. Diodes are pretty versatile. We use diodes in almost every electronic devices, and they're pretty handy when it comes to circuit design. But it's important to know the type of diode that you want to use for your application. So in this case, what I'm trying to do, I'm trying to regulate this output voltage to a fixed voltage. So regardless of what current I'm drawing out of this out pin, this voltage stays consistent. You guys recall that in the previous case where we had 2 resistors or a voltage divider, the output voltage went all the way down to minus 70 something volts, right? Which is not good. So now kind of a diode that I use is a Zener diode. So how do I select the Zener diode in LTspice? I again hover over this component, right click, go to pick new diode, and LTspice basically opens up this long list of diodes that you could choose from. There are so many different manufacturers, so many different types. These are silicon diodes, which are basically just used for general purpose diodes for basically blocking the reverse current and all that. You could use Schottky diode, which is pretty much the same as a silicon diode, but they have faster response, so they react much quicker. Or you could just use Zener diode, which is used for voltage regulation to create a voltage reference on a node. Or you could use LEDs. So in this case, we want to use a Zener diode because we want to be able to create a reference voltage and we want to be able to keep the voltage at a certain value. LTspice hasn't actually added a 5-volt Zener, so the closest one I can find right here is a 6.2 volt. There are tons of 5-volt Zener diodes that you could choose from, but again, for the sake of this simulation, I'm just gonna go ahead and select a 6.2 volt Zener diode. So I hit OK, and then you see that this particular part number corresponds to this Zener diode that is from On Semiconductor, and it has a breakdown voltage of 6.2 volts. So what does it mean? It means that if this Zener diode gets enough current, which is again is set by this 200 milliamp, it turns on and it makes sure that the voltage at its cathode, which is out in this case, is always at 6.2 volts. Again, this voltage can oscillate a little bit based on temperature, based on different parameters. We don't want to get too much into nitty-gritty of that, but this voltage is going to be at 6.2 volts. So now what does this R1 resistor do? So the purpose of this resistor is to make sure that we don't burn out this Zener diode. So if you think about it, now the voltage across this resistor is 12 volts minus 6.2 volts, and then it'll be divided by the amount of current that we're supposed to source, right? So this is going to be 200 milliamp through this whole circuit. It goes from the source, it goes from R1, and then it goes directly out to this load. So that's how we find an R1 value. For example, let's say in this case, since we want to have 200 milliamp output current and we have a 12 volt battery and the Zener is at 6.2 volts, now an ideal R1 value would be about 29 ohms. So I'm just going to put 29 ohms. 29 ohm is not a standard value, but we're just going to assume it is for the sake of this video, and we're just gonna go ahead and rerun the simulation. So now the voltage at battery is still at 12 volts, but then now the output voltage, as you can see here, is set to 6.178. The current, you could change it to anything you want. You could change it to any value you want. Obviously, you got to be careful about the power dissipation, but you could change this current to anything you want. But the Zener diode ensures that the voltage at this out pin is always at 6.2 volts. So now that you have this circuit, you know that for a fact you get a reference voltage of 6.2 volts, and you can sync 200 milliamp through this model. And again, you could see that here in this case also modeled the power dissipation of this R1 resistor. As you can see, it's pretty substantial. It's about like 1.17-ish watts, which is pretty substantial. So you need to be careful that you have enough copper around it. You have thermal techniques that you could implement in order to increase the area for heat to dissipate across this resistor, which in turn lower the resistivity of the current path, which means that it's going to bring down the amount of C, or the amount of heat that the circuit generates. And as we calculated it, this 29 ohm resistor ensures the 200 milliamp of current through it. So this is it for the sample circuit that we talked about. But it's important to note that LTspice is not just a tool for simulation. It's also a powerful analysis tool that can help you dig deeper into the performance of your circuit. With LTspice, you could perform a wide range of analysis, as we said, including AC, DC, transient, and noise analysis, among other things. We could get to other types of directives that LTspice provides that can be helpful for designing EMI filters. It can be used for designing op-amp filters, analog filters, as well as so many other designs that can be helpful when it comes to complex and mixed signal boards. Hopefully this LTspice video kind of helped you guys get a better understanding of what LTspice actually does. And I believe LTspice has a pretty intuitive interface and easy to use tools. As we discussed, you could use your mouse and keyboard pretty quickly to interact with so many different parameters, so many different tools to use in LTspice to simulate your circuit. So whether you're looking to simulate a simple circuit or analyze the performance of a complex system, LTspice is an essential tool for any electronic engineer. And with this brief introduction, you will be well on your way to mastering the power of LTspice. Thanks again guys for watching. Stay tuned for more tips, tricks, and tutorials on electronics design with LTspice. Let me know your comments and questions down below, and peace.